Oh.
Maurizio's car slams into the concrete barrier, catapulting him out of the window and hurling him through the air. Maurizio's car slams into the concrete barrier, catapulting him out of the window and hurling him through the air. Catapulting him out of the window and hurling him through the air. Hurling him out of the window.
Okay, so what's pushing him in the direction that he's flying? Okay, guys, just feel free to jump in.
Barrier, catapulting him.
All right, so what's pushing him in the direction that he's flying?
Out of the window and hurling him.
Any ideas?
Catapulting him out of the window and hurling him.
He's getting catapulted
through the air.
What's pushing him in the direction that he's flying?
The concrete barrier, catapulting him out of the window and hurling. Catapulting him out of the window and hurling him. Catapulting.
So what's pushing him in the direction that he's flying?
Is it inertia?
I'm sorry, say it again.
Inertia?
Inertia, is inertia a force? It's not. So give yourself 5 points. So what's pushing him in the direction that he's flying?
Him out the window and hurling.
This guy's flying. What's pushing him in the direction that he's flying? What's pushing him in the direction that he's flying? He's not connected to anything, right? So if that's the case, what's pushing him in the direction that he's flying? What's pushing the ball in the direction that the ball is flying horizontally?
Force.
Okay, what is the force making the ball go horizontally once it leaves my hand? So what's pushing the ball in the direction that it's flying? The answer to that question is nothing, nothing, nothing. All right, so if there isn't anything pushing on the ball in the direction that it's moving, why would the ball keep on moving then? I mean, my car, when it runs out of gas, it doesn't move. Your car doesn't move. So how come the ball keeps on moving despite the fact that there's nothing pushing on it? Create a project from a Chicago student. If it looks like it's done over a lunch break, because it is, that's what the guy told me. It's hitchhiking. I recognize the guy, so I'm giving him a ride. And this is my Ford Tempo falling apart as usual. This was like almost 15, 20 years ago. So you accelerate in the forward direction. The person inside feels a push in the backward direction. You put the brakes on, now the person feels a push in the forward direction. Why is it that the objects inside cars move in the opposite direction of the acceleration of the vehicle? Why do you feel a push in the backward direction when the car accelerates forward? Why do you feel a push in the forward direction when the car accelerates backward? How about a head-on collision between a car and an SUV? Which one is going to experience a larger impact force? Is it the car or is it the SUV? What do you guys think?
The smaller car.
Okay, so common sense, I'm going to give you 5 points for that one. Smaller car is going to suffer the most damage, right? All right, so why?
Because the SUV has a bigger mass.
Okay, so SUV is much more massive. Give yourself 5 points. So which means that the damage on the smaller car is going to be bigger. Okay, what else? All right, so which driver is going to be safer in this case? Obviously, the SUV driver is going to be safer. All right, so let's come up with 3 reasons as to why the SUV driver is going to be safer. Reason number 1, the SUV is much more massive, right? It's heavier, so that helps. Okay, what else?
Well, with it being more massive, it's going to have more crumple zones in it.
I'll give you 5 points. And also, it's got a larger crumple zone, right? So that's going to increase the impact time. All right, one more. So it's more massive. It's got a larger crumple zone. So we got 2 so far, and we need 1 more, people. How about the fact that the SUV driver is sitting higher up? All right, so that's going to help because the force is not directly in line with the driver. All right, so being higher up actually helps you better. So that's not going to be direct impact to his body. So three reasons. SUV is much more massive, heavier, larger impact zone, larger crumple zone. It's going to increase the impact time. On top of that, the driver is sitting higher up. So the driver is not in line with the impact force. So those are the factors. All right, so the next question is which vehicle is going to experience a larger impact force? All right, so once again, we went back to the same question, and common sense will say it's the smaller car because the damage is much bigger on the smaller car. Okay, who wants to disagree? Who wants to say both will experience the same impact force? I know some of you guys have taken high school physics, so those of you guys who've taken high school physics will get to disagree at this point. So which vehicle is going to experience a large impact force?
Neither.
Okay, so Jack, you said neither. Okay, Jack, are you confident enough to defend that both of them will experience the same impact force? Do you want to make an attempt?
I can certainly make an attempt.
Okay, okay. So, how would you justify that? Okay, so both will experience the same impact force because complete that sentence.
They'll both experience the same impact force because they're slamming into each other. It's not like they're each separately hitting a tree, they're both hitting this like each other, and so I think the force will be shared amongst that whole collision.
Okay, so I'm gonna give you 5 points. Jack, have you taken high school physics?
Yeah,
Okay, you've taken physics before. Okay, so do you recall Newton's third law, the action and reaction law? Okay, so that's known as karma, right? Being a bitch. So for every single action force, there's going to be an equal and opposite reaction force, right? So if Newton's third law is correct, both vehicles should experience the same force. So whatever the force acting on the small car should be acting on the big one. So whatever the small car experiences, the SUV is going to experience the same thing. All right, so this is the summary of the third law. All right, so having said that, Jack, so what I'm going to do is I want you to defend the third law. In a sense, every time I'm just going to take this simple scenario, I'm going to make it a little bit more confusing, and then I'm going to make it a little bit more twisty, in a sense that I'm going to make it a little bit more challenging. Okay, so in the meantime, what I want you to do is every time I change the scenario, say both of them will experience the same impact force because of Newton's third law. Can you do that?
yeah.
Okay, cool. I mean, just you will get confused. I don't want you to give up. All right, I'm going to try to confuse you. Just hold your line. Newton's third law because of Newton's third law. Same force because of Newton's third law. Action and reaction forces are the same because of Newton's third law. Okay, so just follow back to that position, regardless of how confusing this gets. All right, don't change your mind. Can you handle that? Don't change your mind.
You got it.
So Jack, let's go. All right, so which vehicle is going to experience the same? Which vehicle is going to experience a larger impact force? It's the same, right? Because of Newton's third law. Okay, so I'm going to change the scenario. SUV becomes a bus, and this car becomes a smart car, head-on collision. All right. So the amount of force acting on the car is like 100,000 pounds. Will this car apply the same force back on the bus? Yes or no?
Yes, because of Newton's third law.
You got it. Give yourself 5 points for that one. Okay. So let's change the scenario one more time. Okay. Now the bus becomes a train, and then I don't want to waste a perfectly good smart car because of this thought experiment. Instead, I'm going to put you in front of the train. All right. So the train is coming at you at 60 miles per hour. And the train is going to hit you with 1,000,000 pounds of force, 1 million. All right. So will you be able to apply the same force back on the train?
Yes, because of Newton's third law.
Okay. Okay. So you're saying that, yeah, you should be able to, right? Because that's what Newton said. I mean, no one denies that a train can hit you with 1,000,000 pounds of force. And the end result is fairly obvious because you're not going to survive this. At 60 miles per hour, 1,000,000 pounds of force, not survivable. Okay, so what's not convincing is you applying the same force back on the train. When was the last time you applied 1,000,000 pounds of force on something, and how well did that work out? Can you even apply that amount of force on anything? The answer to that question is no. So, I mean, are you going to be able to apply the same force back on the train when you're actually falling apart? A train hitting you, you will literally break apart. You will splatter all over the place. So if that's the case, which one is going to be experiencing a larger impact force? Is it you or is it the train? You want to say, huh?
I'm going to stand my ground here and say.
Okay, you will have to stay on your ground because you're already committed to it. All right, I don't want you to change your mind. Okay, so the question is, you have to go with what Newton said, and Newton will say what? Newton will say, yeah, it doesn't matter what happens to the person still applies the same force back on the train, right? So if that's the case, my question is, where is the evidence? Where is the evidence that you applied the same force back on the train? The reason why I'm asking that question is, Newton lived about 350 years ago. 350 years ago. Did they have trains back then? No. This guy simply didn't see the train coming. So, do you think Newton made a mistake?
No.
All right. So, if you don't think Newton made a mistake, so how do you explain you being able to apply the same force back on the train? And if that's the case, where is the evidence that you apply the same force back on the train?
Well, the train is much more massive. And so the force that applies on me is very clearly physically evident, but I don't know that it'd be so evident in comparison to the train.
Okay. All right, Jack, I'm going to give you about 30 pounds. I'm going to give you 30 points because number one, you held your ground pretty well. Number two, you kind of thought about it and you were thinking, wait a minute, there may be a way to explain this, right? Explain yourself out of this. Okay, so we'll get back to it again. This is a bit of a mind twister. Because Newton says the action and reaction forces should be the same. If that's the case, where's the evidence, right? When you're getting hit by a train. All right, so, clearly we're discussing Newton's laws of motion. So Newton, according to a legend that he himself started, this is a bit of a made-up story. And he told this story late in his life. because somebody wanted to know how he started thinking about gravity, because he came up with the law of gravity, laws of motion. Along the way, he also invented calculus. And according to his story that he himself started, he said he was asleep under an apple tree in his family orchard one day, and then the apple falls, hits him in the head. He opens his eyes. He sees an apple hanging from a tree, and next to the apple, he sees the moon. He knew why the apple fell. It fell because of gravity. His question was, if objects fall because of gravity, why is it that the moon is not falling from the sky? Now, that question became his obsession. In order to answer that question, he first came up with the 3 laws of motion, and then eventually he came up with the law of gravity. And then in order to solve this puzzle, he also invented calculus. He was only 21 to 22 years old when he had done all this stuff. The first thing he did, he borrowed the first law from this guy, Galileo. Galileo was conducting some interesting experiments that he became famous for. Number one, he was in his 70s. He was under a house arrest. And his obsession was this, free fall. Remember free fall, objects falling under the influence of gravity? But he knew the falling objects would accelerate, but he didn't know how to measure this acceleration. The reason why it's so difficult to measure this acceleration is because of the fact that the motion happens real fast. You can't even tell if it's falling at constant speed or if it's speeding up, right? So this guy, being a genius that he was, he decided to slow the motion down. You're thinking, how do you slow it down? He's thinking, oh, it's easy. I'm going to use an incline. So if you use an incline, what do? You roll it down. You roll the ball down. It slows down. It's still rolling down because of gravity. Now you can measure the distances within subsequent time intervals, 1 second time intervals. You look at the distance, measure distance. The second measured distance is going to be larger. The third one is going to be larger. And then eventually, by modifying mathematics, you can figure out what that acceleration is. Something that we will do later on. So when he was doing that experiment, all of a sudden he noticed that something interesting, intriguing. So he's an old guy, so he had one incline, the second incline to catch the ball. And then he lets the ball go down, and then the ball just keeps on rolling and goes back up to the same point. I mean, if you ignore the effects of surface friction, the ball is always going to go back up to the same height. He says, that's weird. It puts the second incline further away. Once again, the same observation. His question at this point is, what's happening when it's on a flat surface? What's happening when it's on a flat surface is this ball keeps on rolling, right? It keeps on rolling. It keeps on rolling in a straight line at a constant speed. So the question is, what's pushing the ball in the direction that it's rolling, if that's the case? What's propelling the ball in the direction that it's rolling? The short answer is nothing. Nothing is pushing on this ball. There's no push acting on it. There's no force acting on it. There's no pull acting on it. Yet this ball keeps on rolling in a straight line at a constant speed. He says, if you were to get rid of the second incline and get rid of all the obstacles in front of the ball and ignoring the friction surface, this ball is going to keep on rolling in a straight line at a constant speed forever and ever and ever. The question is, why? What's pushing the ball in the direction of the motion, in the direction of this motion? If nothing is pushing on the ball, and obviously nothing is pushing on the ball, why then the ball keep on rolling in a straight line at a constant speed? The answer appears to be fairly straightforward. He said, the ball is going to keep on rolling in a straight line at a constant speed forever and ever and ever in the absence of an external force because it's got a tendency to do so. All right, objects have a tendency to retain their initial motions. About a generation later, someone named Descartes decided to call this inertia. Descartes is a French philosopher and a mathematician. So the person who coins the term is Descartes. The person who came up with the concept is Galileo. So what's the meaning of inertia, if that's the case? Well, inertia means two things, and a tendency to retain initial motion, or it means resistance to change in motion. Okay, which means that the object at rest, in the absence of an external force, is going to remain at rest, and the object in motion is going to remain in motion, meaning that it's going to keep on moving in a straight line at a constant speed forever, unless acted upon by an external force. So in the absence of an external force, the objects will retain their initial motions. Object at rest remains at rest, the object in motion will remain in motion.
An obstacle as common as a mailbox can be absolutely deadly.
Mailbox wants to stay at rest, so which means that there's going to be a resistance to change.
To attempt a dramatic stand-up.
This person
Attempt a dramatic stand-up.
remains in motion.
Stand-up. Attempt a dramatic
The car is going at 20, he's going at 20
stand.
when he jumps. He's not connected to the car. He's maintaining his horizontal motion. He's falling under the influence of gravity, but horizontal motion is independent of the vertical motion. So he's maintaining a constant speed. If you were the driver, you can speed up, he won't be able to keep up with that. You can slow down, he won't be able to keep up with it. You can change direction, he won't be able to keep up with it.
Stand-up. Dramatic stand-up.
If the car accelerates in the forward direction, because you won't be able to keep up with it, you will move backward relative to the car. If you push the brakes on as you're jumping up, this time as the car is slowing down, you're going to be moving forward relative to the car. If the car changes direction, you're going to keep on moving forward in the opposite direction of the acceleration of the car again. Do you notice that his body is always going to move in the opposite direction of the acceleration of the vehicle, despite the fact that he's not attached to the vehicle?
The first law of motion.
Could you tell us about that?
It states that an object at rest wants to stay at rest, and an object in motion wants to stay in motion. Property of matter by which it keeps its rest or speed. Okay, let's start with an object at rest. Have you ever seen somebody pull a tablecloth out from under a set of dishes and the dishes didn't move?
I've never been able to do it, and I've broken a lot of very expensive dishes in some very expensive restaurants trying.
Well, the plates have to be heavy, and the tablecloth have to be pretty smooth, and you have to pull it really fast, but it can be done.
But what does that prove?
Well, the dishes are at rest, and they don't want to move. They would rather just sit on the table.
And so what's the motion part?
An object in motion wants to stay in motion. That's why we wear seatbelts in a car.
Oh, I get it. Wait a minute. No, I don't.
Well, if you're in a car,
Could I get a ride? I gotta return my video I rented.
sure. Anyway, if the car's in motion, then you and Red are in motion.
It's a video, so you passed it.
If the car stops, you don't stop. You move forward. That's why we wear seatbelts, to stop us from flying forward.
Okay, guys, put your responses in the chat. All right, so let's get moving. All right, so inertia is the tendency to retain initial motion. Motion means velocity. Velocity is a combination of speed and direction. All right, so this tendency is going to come about only in the absence of an external force. So the tendency to retain initial motion in the absence of an external force. All right, so let's say net external force. All right, so I'm going to put the emphasis on net external force. So only in the absence of a net external force, the object is going to get to retain its initial motion. So motion gets retained, which means that if the object is moving to begin with, it's going to keep on moving in a straight line at a constant speed. If the object is at rest, it's going to remain at rest. So tendency to retain initial motion, that's one interpretation. It's going to have a second interpretation. The second interpretation is going to say resistance to change of motion. All right, so that also means the resistance to change of motion. All right, so resistance to change of motion. All right, so it's got two interpretations. One of them is the tendency to retain initial motion. The second one is the resistance to change of motion. Tendency, resistance. Tendency to retain initial motion, resistance to change of motion. And this behavior exhibits itself only in the absence of a net external force. So two interpretations: the object at rest is going to want to remain at rest. The object in motion is going to want to remain in motion.
So how's that diet coming?
All right, so this is a Super Bowl commercial. Car accelerates in the forward direction, non-strapped objects will move backwards. You put the brakes on. Acceleration is backward. Unstrapped objects will move forward in the opposite direction. Nice Heimlich move. He's regretting that decision of saving his life. Speaking of commercials.
The Lexus GS400.
All right, this commercial is almost 20 years old. Today, the commercials are 0 to 60 within 4 seconds, 3 seconds, or so forth. Back then, they used to make smart commercials. what they're saying is the acceleration of this car is just so incredibly great that even your brain is not going to be able to keep up with it. Neither are your eyeballs. Now that's a smart commercial. A few years later, they came up with even a better commercial.
The quick, remarkably agile Lexus GS. Use it as you see fit.
Acceleration of this car is simply so great, not even a fly is able to keep up with it.
And their
So unstrapped objects inside vehicles,
ability to record
why do they keep moving in the opposite direction of the acceleration of the vehicle?
usable data was limited. Then the U.S. government mandated auto safety testing in 1966. And
A dummy the size of a 3-year-old in the front seat of a minivan was looking back at a 6-year-old in the back seat. Neither is built in.
All right, so it's a crash testing at 40 miles per hour. So the vehicle is moving at 40, and everything inside, everything on the inside, everything inside the vehicle is also moving at 40 miles per hour.
At impact, both
All right, so as the impact starts, the car is slowing down, and notice that the dummies are going to keep on moving at 40 miles per hour.
dummies
They're simply maintaining their initial motion. That's it, inertia. Tendency to remain in initial motion is the reason why unstrapped objects on the inside will keep on moving at the initial speed of the vehicle.
are launched
So they will go all the way up to the dashboard, and they will hit the dashboard at 40 miles per hour.
into the dashboard and then bounce
So what's pushing them in the direction of motion? Nothing. What's pushing them in the opposite direction of the acceleration of the car? Nothing. They're simply maintaining their initial motion.
off the windshield. 65% of
The car is moving at 40. Everything is moving at 40. The car is slowing down, and strapped objects will keep on moving at 40 miles per
children
hour
ages
in the opposite direction of the acceleration
4 to 8 who
because of inertia.
die in car accidents are unbelted. And watch this chilling scenario.
All right, so the objects will fall off.
Children riding unrestrained in the back of a pickup truck.
So the vehicle changes direction. The dummies keep on moving in a straight line at a constant speed in the direction of motion
It
as they're getting pulled down by gravity.
happens more often than you think.
All right, so inertia is,
and their ability to record
Riding unrestrained
I think this is one of those concepts that I ended up discovering on my own when I was 3 or 4. Remember, guys, in the cartoons, you can make this 90-degree turn on your tricycle. So down a hill, I used to try to make those turns, only to realize that it's impossible. You always spill over, and then you get bloodied a little bit. So I would try and try and try. I used to get so frustrated. You can't make those kind of turns in real life
in the back of a pickup truck.
using a tricycle
It happens
because you got inertia. So you got a tendency to go in a straight line
Not
at a constant speed.
in outer space, on a spacewalk.
Oh, can I be in this example?
Okay, so you're in space holding a toothbrush.
A toothbrush?
Yeah,
Is it mine or did I find it in space?
it's yours. You took it for this experiment.
Oh, okay.
Now, as an astronaut in space, you're attached to the spacecraft by a strong cord. But if you let go of the toothbrush, do you know what would happen? It would just stay there. That's right, because an object at rest wants to stay at rest. And what would happen if you gave it a little push? It would start moving and just keep on going forever and ever and ever.
You mean until it slowed down? Right?
No, I mean it would just keep going for like 1 trillion miles and more.
That's a good toothbrush. I should have kept it.
You see, there's nothing in outer space to slow it down. There's no air, no resistance, no friction.
What do you mean?
Friction comes from things rubbing against each other, like the skateboard. The reason it slows down and stops is because the wheels are rubbing against the floor, creating friction. Even the air in here slows the skateboard down.
All right, so ignoring friction, in the absence of any other external force, objects will retain their initial motion. Object moving is going to keep on moving straight down at a constant speed forever and ever and ever. That's inertia.
Buenos Aires, Argentina. It's just before starting time at the Gran Premio de Balcarce race. Driver Maurizio Tucci and his crew are preparing for his run. At the drop of the flag, they're off. Maurizio is at the back of the pack. But as he enters the straightaway, he is about to face the most terrifying moment of his life. Maurizio's car slams into the concrete barrier, catapulting him out of the window and hurling him through the air. Watch again. As the car rolls over, Maurizio flies out and slams against the racer. The impact knocks his helmet off his head. 50 feet down the track, Maurizio's body slams to the ground. Rescuers rush to the scene, expecting the worst. Among them is a friend who is filled with remorse. Earlier that morning, he gave Maurizio his last rites as a sick joke. But he could not have predicted that just a few hours later, his buddy would actually be fighting for his life. Maurizio is seriously injured with 14 broken bones, but by some miracle, he survives. His buddy Maurizio, his last rushed to the scene. Maurizio, his last, could not have predicted that just a few hours later, his buddy would actually be fighting for his life.
All right, so what's pushing him in the direction of motion? Nothing, right? In the horizontal direction, he's going to keep on moving at a constant speed. Ignoring air friction, there's absolutely no reason for him to go any faster or slower. So which means that he's going to maintain his initial motion along that direction. So we got that. Question is, how did he survive? How did he survive the impact? Okay, so I need 5 reasons as to how he was able to survive the impact. How did he manage to survive the impact?
Maurizio is seriously injured with 14 broken bones.
What helped him to survive impact, guys? What made this survivable? I need 5 different reasons. The reason why this guy is still alive because it's a combination of 5 different things that happened. So what are the 5 things that helped him survive impact? Survive the impact.
Does it have anything to do with that? It was spread across multiple impacts because it kind of bounced.
Okay. I'll give you 5 points. I still want 5 reasons as to how he survived. Okay, so which means that I want more than what you just presented. How would you answer if this were a test question? How would you guys answer this? All right, the way he landed.
Impact time?
Impact time. Yeah, what increased the impact time? Hey, is it Ayla Mendoza?
Yes.
Okay, cute. All right, the way he landed. All right, absolutely, guys. The way he landed. He didn't land on his head, obviously. All right, I need more. What increased the impact time? That's what I'm getting at. Okay, so number of factors increased the impact time, right? Go ahead.
The surface area in which the larger surface area?
All right, the way, okay, so he probably had it. Okay, look at the landing. Oh, man, instead of landing, he ended up landing on his back a little bit. Okay, so not the most favorable impact, but that certainly helped. Okay, I'll give you 5 points for that one. I still need 5. What increased the impact time? All right, guys, along the y direction, he's falling from this height, maybe about 3-4 feet above the ground. Okay, so from that height, you should be able to survive the y component. Along the x direction, he didn't come to a stop immediately, did he? He kept skidding and rolling. So notice that the impact time along the x was relatively large. What else?
Rescuers rush to the scene, expect 50. Watch again. As the car rolls over, Maurizio flies out and slams against the racer.
Okay,
The impact knocks
against the racer.
His helmet
It got separated, but the helmet obviously helped, right, with the initial impact. So initial impact, because he ended up hitting the car as he was actually. His head is right now, I think. No, the helmet got separated right there. Either way, I think the first and the second impact, the helmet helped. So the helmet definitely helped in this case. All right, so what else? Along the x direction, he's not coming to a stop immediately, so the acceleration is reasonable. Along the y direction, the height was accurate, so it's not that high. This guy's still moving fairly fast. He's going from, God knows, almost 100 miles per hour to 0, guys.
50 feet.
Long enough impact time, but once again, evidently it was survivable. What else?
Down the track, Maurizio's body slams to the...
Eventually comes to a stop. What else was a factor? He was out. He was unconscious. He was limp. That helps muscles when they are relaxed. So the muscles will increase the impact time. What else? He's got 14 broken bones. Every time you break a bone, that's your crumple zone. So that's gonna increase your impact time. So these are the factors going into it. On top of that, what is he wearing? Notice that he's got this specially designed gear for that purpose. He's got the right outfit. Yeah, he's covered the helmet. The outfit is important. Okay, if he didn't have this outfit, if he didn't have this proper gear, what would have happened? Against concrete, against friction, you're looking at almost instant liposuction. You need to have something that protects your skin, so he had that. All right, so those are the factors that went into survival, and that's
Rescuers rush to face the most terrifying moment of his life.
Now, imagine instead of him driving, imagine. Oh, by the way, why did he get thrown out of the car? Why did he get thrown off the car? All right, you don't think he was wearing a seatbelt, right? Okay, a lot of you guys, your first reaction is he's not wearing a seatbelt.
Starting time at the Grand Premiere.
One of the things that I want you to notice is, I think this is from Argentina. These people obviously want to race. These are not race cars. I don't think any of these people have $1 million lying around for a race car, actual race car. All right, so what do? These are not race cars, guys. These are like super for tempos. Obviously, these guys want to drive. They want to race. They want to have a good time. But at the same time, the safety is a factor here, right? How do you know? They're wearing the right gear. On top of that, everyone is required to wear a helmet. So, which means that the seatbelts are not an option.
Cars a race.
So obviously,
drop of the flag. The impact knocks it.
What happened was the seatbelt was not able to hold them in place. Race cars, you have harnesses. You get into an accident, your body's not going to fly out of a race car. These are commercial cars. These cars are not built for racing. Okay, so if you have a Super for Tempo, that's what you have. You got a Super for Tempo. It's got safety measures which are designed to keep you safe at reasonable speeds. If you're driving at 120 miles per hour, guys, you're on your own. You get into an accident, two things will happen. Either you will go through the seatbelt, or the seatbelt is going to break. So given an option, the engineers will always make sure that the seatbelt is going to keep you in place at reasonable speeds. If you exceed reasonable speeds, the best thing to do is to find the body in one piece. I think everyone agrees on that. All right, no one wants to have an open casket funeral with the head missing. Okay, that's not an option usually. It's not a pleasant option. It makes it look much worse. All right, if it's not survivable, it's not survivable. So they'll just let you go. So what happened here is the seatbelt obviously was not able to hold him in place.
Helmet off his head.
He somehow was able to go through the seatbelt, or don't like the seatbelt broke. All right, so now I want you to use your imagination. Imagine that instead of him driving the vehicle, you got a very tall, 6 feet tall feather who's doing the driving. Exact same accident. Accident is going to be 100% the same as the accident that you saw. Do you think that the feather is also going to rip through the seatbelt? Yes or no?
No.
Okay, you said no immediately. Why did you say no? Okay, you don't think that
you said feather, right? Feather?
I said feather, yeah, but I made it as tall as like 6 feet, so I think that's tall enough, right?
The mass.
You're saying that it's not the size of the feather that matters; it's the mass of it, right?
Yes.
So you're thinking, wait a minute, the first guy ended up ripping through. Literally, he just ripped through the seatbelt. The feather is not going to be able to do that. The reason you're thinking is because the feather does not have that kind of a tendency. And all of a sudden you go, oh, all of a sudden you make the connection that Newton made. Newton will say, driver is going to go through the seatbelt, but not the feather. Because that tendency to retain your initial motion, according to Newton, is going to come from your mass. All right, so the mass is the measure of inertia. Okay, so if you could just express that tendency using a number, that number becomes your mass. So the bigger that number is, the bigger the inertia is. So more massive something is, the larger the inertia is. That's what Newton came up with. So this becomes Newton's contribution. The first law from Galileo. And he gives Galileo plenty of credit. And then he says, oh, that tendency comes from mass. That's it. So mass becomes the measure of inertia. All right, so this thing has mass. Proper unit for mass is going to be kg. The conversion factor for mass, instead of using kilograms, what we use in the United States, we use pounds in the United States. So 1 kilogram of mass is the same as 2.2 pounds of, I was going to say mass, but that's not correct. It's called 2.2 pounds of force. We end up using mixed conversions in the United States because of the simple reason that the original unit of mass was slugs. Slimy little creature, so no one is using slugs anymore, obviously. So that's the reason why we end up using mass in terms of pounds. So we express mass in terms of its weight in essence. So 1 kilogram of mass is going to be expressed in terms of 2.2 pounds of force. Okay, so let's get out of there. In return, this is going to cause a little bit of a confusion, so I'm going to let you dive into the confusion. All right, so the original unit is going to be slugs. Instead, we use pounds in the United States. So 1 kilogram of mass is the same as 2.2 pounds of weight in essence. All right, so bigger the mass is, the bigger the inertia is. Smaller the mass is, smaller the inertia is. So big mass indicates a big tendency. Small mass indicates a small tendency to retain that initial motion. All right, so pick out the best answer. And then put it in the chat. All right, so the amount of inertia that it contains is the best answer, so I'll give you a plus 5 points for that one. speaking of masses, take a look at the penny and take a look at this super tanker. You see the penny? Now take a look at this super tanker. We've got the super tanker. All right, penny is obviously, you know what a penny feels like in your pocket. Let's talk about the super tanker. All right, let's do some mind games. This one is going to be cute. All right, so we'll be doing a bit of a mind twister thing. All right, this super tanker, I'm looking at the number. This is 150 million kilograms. That's 330 million pounds, guys. That's 330 million pounds. 330 million pounds. This is going to be heavier than most of the buildings. This is going to be heavier than your home. This is going to be heavier than one of the biggest buildings at school. This thing's heavy. So 330 million pounds, which means that this thing is incredibly heavy. All right. So it's in water, and it's super heavy because it's a super tanker. So I'm going to give you a rope to tug on. So the rope is going to be tied to the super tanker, and I'm going to ask you to tug on it as hard as possible. When you tug on it, do you think you're going to be able to move the super tanker by tugging on it? Yes or no? The answer to that question is, what do you guys think? Do you think it's going to move when you tug on it?
No.
Okay, but most of you guys will say no. You're not going to be able to make it move. It's not going to move. This thing is heavy. It doesn't matter that it's in water. It's not going to move. All right? It doesn't matter how hard you tug on it. It's not going to move. It's not going to budge. No way it's not going to move. Why not? It's not going to move because it is heavy. Not only is it heavy, it's super heavy. It's not going to move. It's not going to move. It's that heavy. But what if I make it weightless? How do I do that? Well, it's simple, guys. Here's my plan. I want to take it out into deep space. When you take it out into deep space, it's going to become 100% weightless. It's going to become 100% weightless. This thing is going to weigh less than a penny in your pocket. Got it? So this thing in deep space is weightless. This thing is going to weigh less than a penny. Yeah, it is huge. Do you get it? It's huge. I get it. It's huge, but it's weightless. It's got paperweight. It weighs less than a paper. It weighs less than a penny. So the size doesn't matter. I'm going to construct a platform out of metal for you, and I'm going to give you some magnetic shoes so you got your footing. Now that you have your footing, I'm going to give you the same rope to tug on. Will it move now when you tug on it? Yes or no?
I think no.
How much does it weigh?
Nothing. But
It weighs
it's
nothing, right? So can you move a penny? Yes or no?
yeah.
You don't have a problem, right? So if something weighs less than a penny, your initial thought is, oh, it's going to move fine, right? But your second thought is, wait a minute, something is off here, right? So what is it that you're seeing that most of us are not seeing that makes it disagreeable?
So just because the weight's nothing, the inertia is still there. The mass is still there. The resistance to change in motion is still there.
So Jack, you're thinking that that's probably weight. Yeah, it is weightless, but you're thinking that it may not move despite the weight? Because I can tell you what most people are thinking. If it's weightless, it's going to move regardless, especially in space. All right, so let's investigate. A lot of you guys are thinking, wait a minute, you can move it here on Earth while it was in water because it weighs more than the buildings where you work, for God's sake, and now it's weightless. It weighs less than a penny, and you know you have no problem just moving a penny around. It's in your pocket. You just grab it, you flip it, you can do whatever you want with it. It's huge, but the other thing is it's like paperweight. Who cares, right? All right, so just because something is weightless doesn't mean that you can actually move it. You're thinking, oh, here's my opportunity to play Hulk in reality, right? You grab the rope, you tug on it, and then you grab it, you spin around, and then you just let it go. You let it fly, right? You get to play Hulk. You can capture it on video, put it on TikTok, Facebook. You'll get a lot of likes. Life is good. So that's what you guys are thinking. If that line of reasoning is correct, then look what happens. Those of you guys who are a little bit confused about what's going on, it's kind of weird when it comes to the weight and mass. Because of the way we express mass in terms of its weight, in terms of the object's weight, you guys have this very strong correlation between what mass is and what weight is. And you have a way of defining what mass is in the way, how much something weighs. In reality, you know the answer when I ask you a really simple question like, hey, which one is heavier? You've just seen the experiment. And then you go, oh, the one on the left is heavier. And then I say, which one is more massive? You will say the one on the left is more massive. Okay? Because against the same external force, this one was able to persist longer. All right, this one had a larger tendency to keep on rolling. Your mind makes these computations real fast without you noticing. But at the same time, your mind is a prisoner of your knowledge. As far as your knowledge is concerned, mass and weight are correlated. Okay, weight defines how much mass you have. And that's, you make that correlation because of the simple reason that we have a tendency to express everything, every single mass by its weight in the United States. And that's the reason why you guys aren't able to separate yourselves. When I make something weightless, and all of a sudden you go, wait a minute, I should be able to move it around because that's what your mind says. All of a sudden, I was able to trick you into thinking something which is not true.
When it comes
So here's what I want you to do. We're going to be watching this tiny little clip and look at the way I will describe something and listen to it carefully because you will find the answer in my
to
explanation.
destruction, no plane has ever been totaled in a crash test more thoroughly than this one.
I will repeat what this guy is saying, except I'm going to repeat it differently.
An F-4 Phantom sent hurtling along a 2,000-foot sled track at 480 miles per hour.
All right, this thing is moving at 480 miles per hour. All right, so that's its speed.
The 43,000 pound
It's got 43,000 pounds. Okay, 43,000 pounds to you guys, it represents its weight. To me, it doesn't represent its weight. To me, it represents its inertia. It's got a 43,000 pounds of mass that says, it's got a 43,000 pounds of tendency that says, I'm going to keep on moving at 480 miles per hour. All right, it's tendency to keep on moving at that speed. It's got a 4,300 pounds of tendency to keep on moving in that direction. What that means is if I were to stand in front of this, it would go right through me. All right, so it's got such a large tendency, it would not even acknowledge my presence. Except the problem is now it's going to be going up against the block, which is 1 million pounds.
plane literally dematerialized as it plowed into a 1 million pound, 12-foot thick.
You're thinking, oh, that thing is heavy. It's 1 million pounds. Well, that's not what it says at all. It says it's got a 1 million pounds of tendency to retain its initial motion. What that means is it's not moving, so it's not gonna want to move. It's got a 1 million pounds of tendency that says, hey, I'm going to resist in change of motion. I'm going to resist to change of motion, which means that I'm not going to want to move. It's got 1 million pounds of tendency that says, I'm not moving unless you can make me. And this has got a 43,000 pounds of tendency that says, hey, I'm going to keep on moving regardless of what you're doing. So what happens?
Concrete wall, leaving behind nothing but dust and rubble. The test,
Now watch the airplane.
commissioned by the Japanese,
All right, so watch the center of mass. Okay, here's what the center of mass is. I want you to just gauge its acceleration.
was designed to see if the
You notice that it keeps on moving at a constant speed in a straight
concrete
line
casing that houses
in complete oblivion. Because this darn thing is just so incredibly massive. It's got 43,000 pounds. That says, I'm going to keep on moving, and it keeps on moving into oblivion. And look at the 1 million pound block.
nuclear power plants would stand up
It's not budging.
to a direct hit by a
All right, both of them are real massive, and they do exactly what mass is supposed to do. Mass gives you that tendency. One of them has a really large tendency to keep on moving into oblivion.
falling jet.
The other has a very large tendency not to move, and it's not moving. It's not because they're heavy. It has nothing to do with it, but because they're extremely massive.
Though the jet disintegrated, damage to the concrete wall.
Have you ever experienced something like this within your own lifetimes? Okay, I'm guessing that most of you guys are late teens, early 20s. So yeah, you have experienced something like this, but you were very little at the time if you were born at all.
Was mine.
That was like 19 years ago, guys, 9/11. I'm not talking about the Twin Towers getting hit. I'm talking about Pentagon getting hit. And a lot of conspiracy theories are, where's the evidence that the Pentagon got hit?
Not all crash
Well, Pentagon was protected just like
tests
that.
take place on the road
Notice that not much left behind.
or in the sky.
You see, here's a small plastic boat moving along at 2 miles per hour. As you can see, I was able to stop the boat with just my hand. Now we see a big ship in a harbor, coasting at about the same 2 miles an hour.
That's a big boat!
Now, not only could I not stop it with my hand, a pier doesn't even stop it.
Whoa, look out!
So you mean that something has the more inertia it has, right?
Hey, you got that one, that's right. Something with a lot of mass might be hard to start moving, but once it starts, it will be hard to stop.
All right, so this brings us to the next point. It's the movie Armageddon.
This is the Earth at a time when the dinosaurs roamed a lush and fertile planet. A piece of rock just 6 miles wide changed all that. It hit with the force of 10,000 nuclear weapons. 1 trillion tons of dirt and rock hurtled into the atmosphere, creating a suffocating blanket of dust the sun was powerless to penetrate for 1,000 years. It happened before. It will happen again. It's just a question of when.
right, so for those of you guys who've seen the movie Armageddon, give yourselves 5 points. The premise of the movie is we have an asteroid the size of Texas coming towards us at about 25,000 miles per hour. It's on a collision trajectory. All right, so remember, guys, this is the size of Texas, but it's coming from deep space. It's weightless. It's 100% weightless. It weighs less than a penny. Given the fact that it's weightless, why not just send out a bunch of astronauts and give them some jetpacks, and then have these astronauts just push this asteroid from its free collision trajectory so that it misses Earth as opposed to just colliding with it. If you can move a supertanker around because it's weightless in space, if you go by that logic, you could do the same thing using this asteroid. You could do the same thing with this asteroid, guys. You're thinking, wait a minute, that supertanker was motionless. It wasn't moving until you started to move it around by using your rope. This thing is coming at you at 25,000 miles per hour, so that means something. What does it mean? It doesn't mean anything. So it's coming at you at 25,000 miles per hour. It's weightless. All right? And something moving much faster than that, light, it moves at the light speed. It's weightless. When it hits you, you don't bounce around. And this thing weighs as much as light does. So why not just send someone out, give this person a jetpack, and have this person just push it out of the way so it doesn't collide with the Earth? Why not do that one?
Proximity of the asteroid and no prep time, none of our primary plans can work.
Why don't we just send up 150 nuclear warheads and blast that rock apart? Terrible idea. Was I talking to you?
This is Dr. Raul Quincy from research, pretty much the smartest man on the planet. You might want to listen to him.
General, if you could consider your target, composition, dimensions, sheer velocity, you could fire every nuke you've got at her and she'll just smile at you and keep on coming. You should know that the president's scientific advisor.
All right, so what that means is this thing is so darn massive, it's gonna keep on moving in a straight line at a constant speed, guys. It's so incredibly massive. There's nothing that you could do to stop it, in essence. Something the size of Texas, it's an extremely large inertia. Just because something is weightless doesn't mean that it's massless. Remember, guys, that mass is the measure of inertia. Bigger the number is, bigger the inertia is.
Suggesting that a nuclear
Bigger the mass is, bigger the tendency is.
blast could change this asteroid's trajectory. I know the president's chief scientific advisor. We were at MIT together. And in a situation like this, you really don't take the advice from medical C- in astrophysics. The president's advisors are wrong. I'm right.
Hitting a rock from the outside will do the job.
Imagine a firecracker in the palm of your hand. You set it off. What happens? Burn your hand, right? You close your fist around the same firecracker and set it off. Your wife's going to be opening your ketchup bottles the rest of your life. You suggested that we blow this thing up from the inside. That's exactly what I'm saying. Oh.
We drill.
All right, so they decided to actually break it down, which means that they decided that they're going to reduce the size of the mass, trying to make it much more manageable. So that's the direction that they decided to go. Just because something is weightless doesn't mean that it's massless. Jack, give yourself 20 points for the comments that you made. In space, the supertanker is going to be weightless, but nonetheless, it's still extremely massive. That's still 330 million pounds of mass. Remember what happened to a 1 million pound a block? It didn't move because it had a tendency not to move when it was struck by an airplane. And now imagine that tendency to be 330 million pounds. So it's going to be 333 times larger than 1 million pounds. So that thing is not going to move in space either, guys. So that tendency is known as mass.
I need to run. I need to be strong. I need to be fast. I need to keep going. I need to remember not to set my Budweiser on the back of some truck. I need a doctor. I need to run. I need to run. I need my Budweiser. I need a doctor. I need.
He's going in a straight line at constant speed. That's inertia. He's maintaining his initial motion. But as soon as there's a force acting on him, you notice that he changes direction, he slows down, which means that his velocity changes. What that means is he actually accelerates. So that's what a net force does, external force does. So when there's an external force acting on you,
I need a doctor.
You speed up, slow down, or change direction in the direction of the external force. That's known as the second law. The first law deals with what happens in the absence of an external force. The second law deals with what happens when they're in the presence of an external force. What happens in the presence of an external force is you do accelerate. External force does acceleration. External force is going to overcome your inertia. It's going to make you go faster, slower, or it's going to make you change direction in the direction of the external force. So force acting on a system is going to cause it to accelerate. Force acting on this mass is going to cause it to accelerate. The unit of force is going to be newtons. So that becomes the second law. All right, so the second law is the force law. Force acting on the mass is going to cause it to accelerate. All right, so force causes acceleration. F is your force, M is your mass, and A is the acceleration. Acceleration is going to be expressed in terms of meters per second squared, as usual. Mass is going to be in terms of kilograms. The force is in honor of Newton. It's going to be newtons. So the force is going to be expressed in terms of newtons. So second law is the force law. Power per unit is newtons. In the United States, we use pounds. So roughly 10 newtons of force is going to be 2.2 pounds. Not to be confused with mass. 1 kilogram of mass was 2.2 pounds as well, except this was a force unit. Got that right. Give yourself 5 points for that one.
是今天下午进行的中原总决赛，大家都在观看着，等待着这一个激动的时刻到来。这位选手。
All right, so the martial artists or the kung fu masters, evidently, according to a lot of the Eastern movies, they can defy the laws of physics, evidently. So this guy is going to try to defy Newton's second law. He's done his breathing exercises. What he's going to try to do is he's going to try to catch this falling tree trunk without accelerating. If he can do that without accelerating, then I'll say, okay, perfect. So this guy can defy the laws of physics. Now, according to physics, let me tell you what the law says. This guy should accelerate in the direction of the external force. So there's going to be an external force acting on him, and he should accelerate in the direction of the external force. Guys, I'm making two statements. One statement is there's going to be a force acting on this person. The second statement is this force is going to have a direction. And the direction of this force is going to set the direction for that acceleration. So defying the laws of physics means I'm telling you what the law is. And if this guy does not move in the direction of the external force, then that's how you defy the law. So physics is obvious. There's a prediction here. Prediction is there's going to be a force acting on him. He will move in the direction of the force. He doesn't have a choice. And according to movie physics, he's just going to do fine because he's done his exercises. He was breathing just fine. All right, he built up his chi. That's what they say. Boom. Well, evidently today, another day to defy the laws of physics. This being 2020, it didn't work out too long.
他已经做好了准备活动，两个眼睛紧紧地盯着这棵树。下一则新闻是今天下午进行的中原总决
I love this guy's excitement.
赛，大家都在观看着，等待着这一个激动的时刻到来。这位选手，他已经做好准备了。
He lined up. He's lined up properly. To catch the tree trunk. And then it looks. He almost tried. Damn, so close. I love the crowd's reaction. A couple of people end up clapping their hands in appreciation. Most of them said, let's move on.
他已经做好了准备活动，两个眼睛紧紧地盯着这棵树。
All right, guys, these are no special effects. No one got hurt. Supposedly, this is a commercial. That's what one of my Chinese students said. I don't know what for, though. Obviously, it's not a Coke commercial. I wonder if it's related to constipation or something like, hey, we can squeeze this shit out of you naturally. All right, so whenever you come up with an answer, all right, but there is a bit of a confusion here. The confusion arises here not because of your lack of understanding of physics or the concept. Your understanding is there. Your interpretation is lacking for those of you guys who didn't get to the right answer. Okay, so imagine that you apply the same amount of force on two different masses. All right, so one mass is massive, the other one is not. All right, I got this ball, so I'm going to apply the same force on this ball and on my car. All right, so which one is going to accelerate more? That's what it says. Which one is going to speed up much more quickly? Translated to English, that's what it means. So what am I doing? I'm applying the same force on this ball as well as on my car. So which one is going to speed up faster? Which one is going to accelerate quicker? Which one is going to have a larger acceleration? And you know immediately that this ball is going to accelerate much more rapidly because it's less massive. All right, so which means that the acceleration of the light body is going to be larger. Those of you guys who pick B, give yourselves 5 points. That's it. Okay, one of the things that I want you to notice about the force is, okay, all of a sudden you realize that your car is driving itself at night, and you know that's impossible. So all of a sudden you realize that it's being towed, right? And you could clearly see that it's being towed because you can see that the tow truck is attached to it, or your car is attached to the tow truck, more like it. All right. So those kind of push-pull, your car being towed, someone pushing on a buck, I mean, you can see the source of the force. There's a clear relationship between force and the motion. But when it comes to gravity, that relationship is not that obvious. Gravity is not something that you could see. So how do we know that gravity is a force? How do we know that the gravity is going in the downward direction?
Oh, Newman.
I hate you. Hate him.
I despise him. Why? I'll tell you why.
Let me tell.
No, you can't tell
You
him.
always tell it.
I tell
I did it. You just tell it.
June 14th, 1987. Mets, Phillies. We're enjoying a beautiful afternoon in the right field stands when a crucial Hernandez error opens the door to a 5-run Phillies ninth, cost the Mets the game.
Our day was ruined. There was a lot of people, they're waiting by the players' parking lot. We're coming down the ramp. Newman was in front of me. Hernandez was coming toward us. As he passes us, Newman turns and says, "Nice game, pretty boy." Hernandez continued past us up the ramp.
Then, a second later, something happened that changed us in a very deep and profound way from that day forward.
He spit on us. Nice screen down the
Then I turned and the spit ricocheted off him and it hit me.
Wow, what a story.
Unfortunately, the immutable laws of physics contradict the whole premise of your account. Allow me to reconstruct this, if I may, from its premise, as I've heard the story a number of times. Newman, Kramer, if you'll indulge me. According to your story, Hernandez passes you and starts walking up the ramp. Then you say you were struck on the right temple. The spit then proceeds to ricochet off the temple, striking Newman between the third and the fourth rib. The spit then came off the rib, made a right turn, hitting Newman in the right rib, causing him to drop his baseball cap. The spit then splashed off the wrist, pauses in midair, mind you, makes a left turn, and lands on Newman's left thigh. That is one magic loogie.
Well, that's the way it happened.
What happened to your head when you got hit? Well, my head went back to the left. Say that again. Back and to the left. Back and to the left. Back and to the left.
What are you saying?
I'm saying that the spit could not have come from behind. That there had to have been a second spitter. Behind the bushes on the gravelly road. If the spitter was behind you as you claim, that would have caused your head to pitch forward.
So the spit could have only come from the front and to the right.
But that's not what they would have you believe.
I'm leaving. Gary's a nut.
The sad thing is, we may never know the real truth.
Okay, notice that they were trying to figure out the direction that the spit was coming from by looking at the motion of the head, the first jerk, the acceleration of it. In essence, what they're doing is they're making fun of the movie JFK. And the movie JFK, those of you guys who've seen it, give yourselves 5 points, is based upon, obviously, the Kennedy assassination investigation. So the movie alleges that there was a cover-up. All right, so most of you guys seen this footage, obviously. All right, so hint, hint, somebody, just a warning, somebody's going to get killed. You're not going to see much. It's not going to be gross. You're not going to see the details, obviously. It's a reconstruction of this footage. All right, so here's the premise of the movie. It's really, really well done. I love the reconstruction of it. All right, so there's a claim that there's a second shooter. And the premise of the movie was there's a cover-up because according to the history, there's only one single shooter. All right, so what do you expect, guys? The objects will have to accelerate in the direction of the external force. So Kennedy takes the first shot. All right, so you notice that his arm just went up. And so his body moves in the direction of the external force in this case, so the force generated by the bullet. And then all of a sudden, everything is going to go behind this little cover, which means that the camera does, I think they're putting in a couple of footage together. And then the second shot, you just saw the second shot. All right, so his head jerks in this direction. All right, so given the fact that the objects will accelerate in the direction of the external force, clearly the movie will claim that there's a second shooter, which is going to agree with physics in essence. All right, so I think this is, we're going to go through the same thing again. All right, so I'm going to move forward. Okay, let's check to see if we can get it better. All right, so I'm going to stop it right here. All right, so he takes the first shot. He's in pain. He's grimacing. And then his head is going to jerk in that direction. You will see a flash of light as soon as we come out of it. All right, so he's in a lot of pain. And notice that, boom, it just lit up. This section lit up. And notice that his body moves in that direction. All right, so what does it mean? I mean, you just saw the explosion right there. So the body's going to move in that direction. So objects move or accelerate in the direction of the external force. So the implication is, the prediction is what physics predicts, which means that there had to be a second shooter. So the question is, was there a second shooter? Which direction did the bullet come from? All right, so let's go back.
Lucky bastard. Jesus!
Immediately you know that the bullet came from his left, right? And then all of a sudden the indentation appeared. And you saw the initial jerk in that direction. I mean, the bullet was moving. Acceleration is in the direction of the force, so the initial jerk is in that direction. It's beautifully done. So by looking at the initial jerk, direction of the initial jerk, initial acceleration, you know that the force causing that acceleration is in the same direction. So that tells you about the direction of the bullet. All right, I'm not sure how many of you guys seen this movie. Those of you guys who have, give yourselves 5 points for it. So it's Private Ryan.
Jesus! Come on, lucky bastard.
I don't know why. I can't stand the sight of blood. And what's weird about it is my dad is a medical doctor. My mom is a nurse. What that means is I should be perfectly comfortable with the sight of blood. I should be comfortable swimming in it. Forget about looking at it. But I simply can't stand it. So I can't really watch these slashers. For whatever the reason, though, the war movies I'm a big fan of. All right, so if there's violence, the violence is kind of like what you just saw there. It's brief. By the time you notice it, it's too late, and they move on to something else. And you know, it's suspenseful, and then obviously you get into it. You get into the adventure of it. Except this movie was different. When the Private Ryan came out, the first 20 minutes to half hour of this movie was set to be so realistic that even the war veterans were having flashbacks. It was that bad. In fact, one of my... Yeah, go ahead.
I just spoke to a veteran who's actually been in combat, and he said the same exact thing about this movie and Hamburger Hill too.
100%. Give yourself 5 points. A friend of mine, this guy was a philosophy professor, and he actually volunteered twice for Vietnam. He said, Canada, he said, the first half hour of the movie, he said, as realistic as it gets. He said, it's a complete clusterfuck. All right, those are his terms. He said, it's just so incredible. He said, you got to go see it. If you want to see something anywhere near as realistic as what a real battle experience is, he said, the first half hour is exactly what it is. He said, you don't know what's going on, and you can't hear anything, you can't see anything, and then there's this mess all over the place. Except the first half hour of the movie, from what I read, was just so gruesome. It's so bloody and so gruesome. I didn't think I was going to be able to handle it. All right. I mean, Hamburger Hill, I've seen it. The violence, when happens real fast. But this thing is like, it's supposed to be really, really gruesome. So I wasn't sure. So I thought about it. I thought about maybe I should just skip the first half hour and then walk in half hour late. So I could make up my mind. So I thought about it for about a month. So I said, okay, I'm just going to go to the movie theater. And then I was going to check myself into a bar and get drunk. And then when I felt brave enough, just walk in and watch the entire movie. Anyway, so I watched the entire movie. Let me put it this way, from beginning to end. The first half hour was bad. It was gruesome. Except I got really distracted because of the accuracy of physics. Accuracy of physics was unbelievably on point. It was so incredibly well done that I couldn't even focus on the violence properly. I could see the guy in the background running around with his intestines sticking out. He's just trying to push him back. And it was bloody. It was, I mean, the gore was all over the place. But the physics was just so incredibly accurate. I had to go back and watch the movie again just for the story. All right, so in terms of the accuracy of the physics, the stuff that I'm going to show you, number one, if you're squeamish like me, you're not going to see any blood. Okay, so I'm picking a scene on purpose. It's almost like a comic strip movie violence. So there's going to be violence, but there's not going to be blood. All right, so this scene. All right, so you're looking at this, going to be a complete miscommunication in different languages. All right, so this is the guy I want you to focus on. All right, you don't have a choice because camera is going to focus on that guy. All right, so notice that other people are going down. Okay, so the shooting is still going on. You can see that the bullets are going through his body. The parts of flesh is flying out. The clothing is flying out. Eventually, it's stopped. Okay, one of the things that I want you to notice is the people who got shot at, they just dropped. And this guy did not even acknowledge that he was just getting shot at. All right, despite the fact that this guy probably took about 20 bullets to his body. He's not moving at all. Okay, so in the video games and most of the movies, I want you to notice that when someone gets shot at, when someone is actually hit, they kind of acknowledge the body jerks in that direction. Or if it's somewhat exaggerated, like in the video games, you will see people actually flying in the direction of the bullet. Here, there's no reaction to it. This guy didn't move. He didn't move at all. He didn't even move an inch. He didn't move a muscle. In fact, go back. When all right, notice that these guys are going to go down. All right, and none of these people fly in the direction of the bullet. He just dropped. This guy didn't even move. Yeah, he's got a backpack, but forget that. His body does not even acknowledge the fact that he's taking all these bullets to the body. All right. In the movies, you would see a little bit of a reaction, or quite a bit of a reaction when they get shot at. This guy didn't move at all. So is this realistic? Spielberg is the director, obviously. All right. And they have probably had footage like this, probably about, I don't know, 3-4 hours of footage that they probably didn't use. But for one of the reasons, they decided to leave this in the movie. All right. So is this really what happens in real life? I got news for you guys. This is pretty damn close to what should happen in real life from a close range combat, just like that. The reason is because these bullets are going so fast, like 1,000 miles per hour, even faster than that. Your body is extremely massive. All right. It's got a large tendency to retain this initial motion. So it's not going to want to move unless there's a force acting on it. In this case, there's a force acting on it, but the duration of the force is just a fraction of a second. So it's not large enough to overcome your inertia. What that means is, you guys know the analogy, right? The heavy dishes on a tabletop, and then you got the tablecloth and you pull it really hard. What happens to the dishes? Nothing. They don't move. Same thing happens to the body. All right. So normally what happens when somebody gets shot at like that, it's if you can stop the heart, the person is just going to end up dropping on their knees and fall down. All right. Unless the bullet makes contact with one of the major bones in your body, you're not going to see much of a reaction in reality. Mythbusters actually tested this by using pig carcasses, and they end up using guns from handguns to military-grade weapons, rifles or whatever. With bigger bullets, these carcasses, they were hanging from hanging from a rope, basically. Carcasses end up moving when they got hit, but their motions were less than an inch. You could barely see the carcasses sway back and forth. So realistically, this is what you would expect to see. Why is this important? It's important. There are two reasons for it. Number one, it's a safety thing. A lot of the times people expect to see when there's a mass shooting or whatever, it's very difficult to make that connection, make that leap. I don't know, like 10 years ago, somebody showed up with weapons over at NIU, walked into a classroom and started shooting. There were almost 100 students in that mega classroom. Initial reaction of students was laughter, one of laughter. They thought that was a practical joke, okay, because they could hear the pop, and then the timing was off. They didn't, so you would normally expect someone who's shot at to fly in the direction of the bullet, so didn't see that. Instructor went down real fast, so this guy turns around and starts shooting at students in general. Once again, the initial reaction was laughter. Eventually, they saw people just dropping down and bleeding, so there was mass panic. Quite a few students ended up getting killed. I don't remember how many, but that was a traumatic event. All right, so basically, you're not going to see people fly. If you see a gun, take measures, obviously. Protect yourself and get out or attack. Find a way to resolve that issue. All right, another thing is human body does not quite react the same way as a ball does. Kennedy getting hit. All right, so evidently you would expect a second shooter, and you almost could see it. There was an explosion. So what happened was the bullet ended up entering from the back of the head, traveled through the brain. The brain is still alive, so it's just activating all these nerves, and the nerves are just convulsing all these muscles all over the place. There was the skull ended up exploding forward, so you end up seeing that flash. And the body, the muscles just convulse in the backward direction. All right, so notice that number one, you expect to see some motion in the direction of the force. You don't see that when it's going through the flash. So that's something that was not visible, because this thing happens so fast. It just goes through the skull, and then it's not like hitting a helmet. The skull is going to give. So it went through the brain. There was an explosion, and the brain was still alive. So it caused all sorts of convulsions in the muscles, and then the body jerked in a weird sort of way. So that's what happened. All right. So it doesn't quite follow the physics of hitting a ball. So that's a little bit different. Okay, I asked you that question before. I'll ask you again. All right. This thing that looks like an upside down ass is going to be a Newton's apple. And when you let it go, what happens to it? It's going to accelerate, right, in the downward direction. All right, what causes acceleration? According to Newton's second law, what causes acceleration is the net force. If something is accelerating, it's accelerating because of the force acting on it. So this mass is going to accelerate in the direction of the force. Do falling objects accelerate? Of course they do. Okay, we discussed that before. So falling objects do accelerate. You can trace out the source. You can trace the force out to its source. All right, let's just do it this way. This is better. All right, by following the direction of the force, and you will notice that this force can be traced to the center of the Earth. All right, so because the apple appears to be gravitating towards the Earth, we call that the gravitational force. All right, so the apple falls because of gravity. So the next question is, how about the moon? Does gravity extend all the way out to the moon? All right, so the moon is located here, and here's what the moon does. It's going to orbit the Earth. All right, it's not a perfect circle, but I don't care. All right, so the moon is orbiting the Earth. That's what we got. It's moving at a constant speed, but it's not moving in a constant direction, so the direction keeps changing. All right, so this moon's speed is constant, but not the direction. We know, because we studied this, the moon is accelerating, and we also know which direction it's accelerating. And you kind of sense for it, because if you're driving like that, you know that the unstrapped objects will move in the opposite direction of the acceleration, so which means that the acceleration has to be directed inward. So we know that the moon is accelerating towards the Earth, right? So what that means is the force causing that acceleration is also directed inward towards the Earth. And all of a sudden you realize that the force that pulls the apple down is exactly the same force extending all the way out to the moon, guys. That's it. If this force didn't extend all the way out to the moon, what would have happened to the moon? The moon would have gone in a straight line and it
fly off in a straight line
forever and ever and ever. That's all of a sudden you fall back to the first law, right? Inertia. In the absence of an external force, the moon would have maintained its initial motion. It would have gone in a straight line at a constant speed. It would have gone in a straight line at a constant speed forever. It's moving at a constant speed, but not in a straight line, which means that the moon is accelerating, which means that there's a force acting on it. And as it so happens, the force that pulls the apple down is the same force that extends all the way out to the moon. So how do we know that? Because this force is also directed towards the center of the circle. What do we have at the center of the circle? At the center of the circle, you have the center of the Earth. This is pulled towards the center of the Earth, so is this one. So the question is the same question that Newton asked when it was 21 or 22. If the apple falls because of gravity, he asked, why doesn't the moon also fall from the sky? Or does it? All right, so that's where we're at. All right, so let's take this one step further. When an object is falling, okay, so I'm just dropping this ball. Is gravity a force? What are you going to say? You will say, of course it's a force, because it causes acceleration, guys. You cannot feel gravity. You cannot see gravity. You cannot taste it. If gravity is the only force acting on you, literally, if gravity is the only force acting on you, you will not even feel gravity. You will feel weightless. And so how do we know that gravity is a force? It is a force because, by definition, because what a force does is acceleration. The falling ball accelerates in the direction of the force, which means that the gravity is a force because it causes falling objects to accelerate. That's it. So the next question is, does gravity extend all the way out to the moon? Of course it does. What would happen if it didn't? If gravity didn't extend all the way out to the moon would have gone in a straight line at a constant speed. We would not have the moon. Immediately, we got answers to our questions. All right, so Newton's obsession was, well, if apple falls because of gravity, and he knows gravity is a force at that point because it causes acceleration, he wants to know, why doesn't the moon also fall from the sky? But at the same time, he knows that gravity extends all the way out to the moon, right? How does he know that the gravity extends all the way out to the moon? Because if it didn't, what would happen? It would have gone in a straight line at a constant speed. And all of a sudden, he's curious. His curiosity is, he knows the apple falls because of gravity, and he also knows that gravity extends all the way out to the moon. If so, his question is, why doesn't the moon also fall from the sky? All right, I see a lot of D's, so D is the best answer, so that's 5 points for that one. So how do we know that gravity extends all the way out to the moon? There are two ways we know it. Okay, so this is also your next test question, because it's intriguing enough and interesting enough. All right, there are two ways we know. Number one, if gravity didn't extend all the way out to the moon would have gone in a straight line at a constant speed. The moon moves at a constant speed, but it doesn't move in a straight line. It goes in a circle. It's almost elliptic motion, but let's say it goes in a circle, which means that its acceleration is directed towards the center. It's centripetal acceleration. Remember, it's directed towards the center, and then the force points in the same direction. So, which means that this motion is happening because of gravity. The moon is accelerating towards the center of the circle. At the center of the circle, you have the Earth. And then the force is pointing towards the center of the circle where the Earth is. So whatever this force is generated by the Earth itself. All right, so this is the force of gravity, extending all the way out to the moon. The car is moving at a constant speed. but it's accelerating, which means that there's enough force acting on the car. All right, give yourself 5 points. Now, here's the question. If gravity extends all the way out to the moon, how do you explain the fact that the astronauts appear weightless in space then? How could that be? So weight is something that comes, weight is the gravitational force acting on you. All right, so the measure of gravity, the effect of gravity on you is known as your weight. If gravity extends all the way out to the moon, can you be weightless in space?
Astronauts eventually adapt to their balance sensors, giving them confusing and unfamiliar information. After a short time in space, the human body actually forgets how to deal with gravity, and instead learns how to balance and move around without it.
If Newton is correct, if gravity extends all the way out to the moon, you cannot be weightless in space between here and the moon. When you're 180 miles from the surface of the Earth, you cannot be weightless in space. And if you're a conspiracy theorist at this point, you will think to yourself, wait a minute, is this thing is completely made up? Or is there a better explanation for it? Sense. All right, so there's got to be a better explanation. Now, imagine that you're in deep space where you're perfectly weightless. All right, so deep, deep space, which means that you're literally billions of light years away from the nearest planet or star. And so you're pushing up against this spacecraft. Your spacecraft, let's assume that's as big as the supertanker that we were looking at. All right, imagine that you got this supertanker that's 350 million pounds and you're in deep space and this thing is 100% weightless and you're pushing up against it. Will it move? Yes or no?
No.
Of course, we discussed that. The last time we said no because it's real massive, right? Just because something is weightless doesn't mean that it's massive. So what does the mass represent? It represents its tendency to retain its initial motion, right? So which means that if it's not moving at all, if it's at rest, it's going to resist your attempt to make it move. All right, so it's going to have a 350 million pounds of resistance against your force. So the question, will it move? Last time we said no, it's not going to move. And this time I want you to make the argument that yes, it's going to move. Who wants to make that argument? Okay, guys, we got like 17 people. Who wants to say that, yeah, I'm going to push against it and you know what, it's going to move? Is it going to move?
Sure.
Okay, so make the argument. You can't say yes or no. You have to say sure because blah, blah, blah. Is it going to move? Bum, bum, bum. Is it going to move? Is it going to move? Is it going to move? Yeah, let me tell you why. Of course it's going to move. Are you nuts? Because there's a force acting on it. What does a force do? The force acting on the mass is going to cause it to accelerate. Is it going to move? Of course. Is it going to move? Yeah, because there's a force acting on it. Got it? So is it going to move? Last time I said no, I'm changing my mind. That's called the learning experience. Is it going to move? Of course. How do we know that? Because there's a force acting on it. That's called second law. First law is going to say the mass is going to resist. The second law says, hey, wait a minute. The first law is all about what happens in the absence of an external force. In the absence of an external force, what do you see? The object is going to maintain its initial motion. If supertanker is not moving, it's not going to move. There's no reason for it to move. The second law says, hey, wait a minute. If there's a force acting on it, what does the force do? It's going to overcome its inertia. It's going to make it move. Is it going to move? Of course it's going to move. Yeah, but it's a supertanker. This thing is really massive. It's 350 million pounds of force. How hard can you push it in deep space? Guys, if you're lucky, you're going to be able to push it with 100 pounds of force. Do you think, what do you think is going to happen? What's going to happen is it's going to move, but it's going to move barely. In fact, if you keep pushing on it for the next 1 million years, it's probably going to go from 0 to about a mile per hour within the next 1 million years, guys. It's almost like watching the grass grow, except in very slow motion. All right, so it's going to move, but it's going to move barely. What do you think is going to happen to the astronaut? So he's going to lean into the supertanker in space. Supertanker is going to barely move, but it's going to move nonetheless. What happens to the astronaut? He's going to he's going to get repelled back, right? He's going to push against it, and all of a sudden, boom, this guy's going to take off in the opposite direction. In fact, you're going to be able to see it. It's going to happen really fast. He pushes up against the spacecraft. And as soon as he does that, he's going to get propelled in the opposite direction. This guy is going to accelerate in the opposite direction, which means that there's a force acting on the astronaut. Got it? He's accelerating, which means that there's a force acting on the astronaut. So the question is, where does the force acting on the astronaut originate from? Where do you suppose the force comes from acting on the astronaut?
It comes from him pushing the tanker.
Okay, so I'll give you 5 points. There are two ways of looking at it. Some of you guys will focus on the obvious. You will say it's coming from the astronaut himself, right? You can say it's coming from the astronaut himself, and some of you guys will say it's just coming from the supertanker that he's pushing up against. Okay, so let's just clarify that real fast. All right, so just put it in the chat. How many of you guys can lift your own body weights? How many of you guys can lift your own body weights, guys? Hello? This is not a trick question.
I could lift the body weight before I had the baby. Does that count?
That's fine. Nope, not me. This is actually none. How many of you guys can lift your own body weights? Okay, that's actually cute. Some of you guys. You guys, it should be just about every single person in this room or at home, whatever, at this Zoom meeting. Most of you guys, most of us, the normal ones, would lift ourselves up with our legs. Jack, give yourself 5 points. Jack didn't get fooled. All right, because immediately when someone asks you that question, you're thinking, oh, we're talking about how many of you guys can lift yourself up. I'm talking about using a bar. That's not what I'm talking about. Now, for those of you guys who can actually lift yourselves up, you just grab a bar and then just pull yourself up completely. Okay. Now, how many of you guys can do? How many of you guys can do pull-ups just like that? Anybody? Okay, Jake. Let's go with you. Okay, I'm gonna go with Jake because he's the first one volunteer. All right, Jake. How much do you weigh? Rough estimate. You can
190.
make something. Say 190. Okay, which means that you can literally do a 190 pull-up, right? Once or twice, it doesn't matter. Okay, so here's what I want you to do, and I want you to video record this. All right, just get on top of the roof of your building, and then I want you to jump because I don't want you to fall and hurt yourself. I want you to grab the other arm, and then I want you to pull yourself up really hard. Do you think it's going to prevent you from falling? No, right? No. It's going to look pretty damn funny, though. I mean, you cannot lift yourself up by grabbing the other arm. So what does that mean? What that means is the force causing the acceleration has to be external to your body. Got it? Remember, I kept saying the external force. Okay, the first lies in the absence of an external force. What happens? The second lies what happens in the presence of an external force. Internal forces cannot cause an acceleration. You cannot grab one arm of yourself and you cannot lift yourself up. It's out of the question. Internal forces will not cause you to accelerate. So that's what Newton is getting at. So the force that propels this astronaut away from the spacecraft is not coming from him. It's coming from the object that he's pushing up against. All right. So he's the one. He originates the contact. All right, he pushes up against the spacecraft in this direction. So that's called the action force because this guy is starting the action. In turn, he's feeling the reaction force acting back on him. So notice that there are two forces at play here. There's an action force acting on the spacecraft. There's a reaction force acting on him. Notice that they have exactly the same value. They got the same exact magnitude, except they are in completely opposite directions. So there's an action force, there's a reaction force. Action and reaction forces have the same magnitude. They are equal in magnitude and opposite in direction. This is known as the Newton's third law. Now, Newton came up with the third law, and there's a good reason for it, because he had to explain where these forces would come from in nature. And then all of a sudden, he noticed that the forces had to come in pairs, which means that there had to be an action force and there had to be a reaction force. So for every single action force, there has to be a reaction force. They are always going to be in opposite directions, and they're always going to have the same magnitude. That's what it means. All right, did you guys see anything wrong with that scene? Did anybody see anything wrong with that scene? Yeah? Not a single person sees anything wrong with it. Say it again?
Like the way he bounced off the car.
I got news for you. It's Brad Pitt makes the money that he makes because he can survive something like this twice in one single scene. No question about it. This is what happens when I'm watching a movie. I don't know. This movie came out like late 1990s or something, or more than 20 years ago. And it's Meet Joe Black. It's a really good movie. This happens during the first 10, 15 minutes of the movie in reality. All right. And then I'm watching the movie, and then boom, I see this. Everything that you just watched. All right. So this is less than 2 seconds long. And this scene is just a 1 second long scene. And then boom, you remember it years later. It's just so god awful. It's so wrong. You go, holy shit, they missed it completely. I mean, when you're watching a movie, you get really distracted. What's so distracting about it is the way Brad Pitt moves, it's perfect. All right, so you took the first impact, second impact, everything is fine. All right, special effects artists got that right. Action force is correct. Action force is correct. Everything is correct. And then I'm looking at the extras. Those guys are doing a phenomenal job. Not everyone is reacting at the same time. Put the sound effects. Everyone is reacting at different times. Not everyone reacts the same way. So the extras are doing an amazing job, which means that the director is taking this stuff seriously. The only person who's dropping the ball here is the special effects artist. He just dropped the ball big time. Amazing. Of course, you don't see it because you're not a physicist. And that's the advantage of education, guys. The more you know, the more you see in reality. All of us experience the same light, but some of us experience it in high definition. You guys are almost like in a position to watch TV, black and white TV. I see everything in full color. And I also see it in high definition. All of a sudden, I look at this, I go, this is just god awful. What's missing here? What's missing here is the reaction force. All right, guys, if van hits a person, action force is acting on this guy, right? How much force do you think is acting on this guy? I would tell you that there's probably almost 10, 15, possibly 20,000 pounds of force acting on this guy. What that means is this guy is applying the same force back on the van. What happens when you apply 20,000 pounds of force on the van? It's going to dent. Do you see a dent on the car, on the van? No, you don't see a dent on the van at all. And then he hits the windshield. What do you think is going to happen to the windshield if somebody hits it like at 20,000 pounds of force?
Shatters.
It's going to shatter. It's going to break. Okay, and then there's no damage on this vehicle either. On top of that, he almost made it sound like special effects artists, more than like the director said something. Say, hey, this is nonsense. So they end up putting this window shattering sound. It made it almost look like they were able to knock the wind out of him. I suppose that there's pieces of glass in this place. It just vanishes. It just vanishes. Furthermore, if you apply the same amount of force on the car is not going to keep on moving in a straight line at a constant speed. The car is going to jerk. It's going to slow down. You don't see it because of the fact that they end up putting sound effects into it. But if I get rid of the sound effects, just watch the cars. All right, just watch the cars again. Again. Do you think there's any impact in reality? If you just focus on the cars, you know the cars are not hitting anything. They keep on moving at a constant speed.
No, once the guy hit the van would have swerved.
Or you would have seen a dent on both of them. All right, so that's what would have happened. So this guy completely, because everything takes place within, literally the entire scene is about a second long. From beginning to the end, it's about 2 seconds long. All right, he doesn't think that anyone is going to notice it. Of course, technology got so much better today. I could just capture it in video and then just keep showing it a million times. And with the exception of physicists, he knows no one else is going to see it. But you can't get away with that sort of stuff. All right, so everything is phenomenal acting. I'm talking about the extras. Director ended up doing a really good job. Special effects artists just completely messed it up. All right, so what happens? Here's what happens.
The object of this game is to not fall off the pole.
Cars are designed to hit you under your center mass. They are designed to hit you under your center mass. Your center mass is your center of balance. All right, so cars are designed to hit you under your center of mass. Your center of mass is your center of balance. Speaking of center of balance, the center of balance looks like this. Okay, this was good. I just want to stop it just briefly so you can see it. Guys, center of balance. Do you see this toy? It's got a center of balance at its peak. At its peak, not the peak, the beak that I'm talking about. All right, so notice that is the center of balance for it. All right, your center of balance is located between your heart and somewhere between your heart and your belly, depending upon how heavy you are. All right, so this person got suspended with respect to the center of mass. So the center of mass is going to be your center of balance, and the cars are designed to hit you over your center of mass or under your center of mass or under your center of balance that you're looking at.
He's run 300 crash tests.
All right, so which means that you're going to get pulled over the vehicle in essence. So that's what it does. So you will get hit right under the center of mass, and then you will get pulled over the vehicle.
Using 2 kinds of instrumented dummies, a small one to represent a child, and a larger one to represent a grown.
You don't want to be hit by a bus, by a van, by a train, because those will hit you right at your center of mass. So when you get hit by the center of mass, you're going to turn into a sideways projectile. So you're going to fly this way. If you're a small adult or a kid, you're going to get hit over your center mass. So when you get hit over your center mass, you will go under the vehicle. That's the last thing you want. All right, so this guy gets projected forward. The kid goes under immediately.
Rusty is on a mission to figure out why some victims are killed outright.
All right, so you're going to get hit right on the center mass. Notice that you get projected in the opposite direction. If it's a high-speed collision like that, you get projected out. All right. The problem with that kind of stuff is obviously the guy is just spitting all over the place, and then he may end up landing on his head. So you're looking at a broken neck. The car is still moving. You can go under the vehicle, get run over. So you got some problems.
Others, like this woman.
All right, a couple of problems with this one. This is a horrible design. The box design, I think this is probably a Russian car, and she's way too short. So she ended up getting hit right at the center of
Somehow
mass.
managed
So she turned into a sideways projectile.
to survive.
Well, there is more controversy surrounding the MTV show that is called Jackass. A Kentucky teen recently broke bones while portraying a stunt seen on the show. Fox reporter Chris Hawes has the story, and a warning now, some of these pictures are graphic.
Okay, guys, warning. The pictures are not graphic. This is just Fox.
Twice,
You're not going to see much of anything.
the cameras show the teenagers practicing what's about to happen. Police say they were getting ready to attempt a stunt they were sure would score them a spot on Jackass, a show on MTV that includes potentially dangerous stunts.
Their stunt was going to be filming a person jumping a vehicle.
The 16-year-old boy stood in front of his friend's car. He would have to jump several feet straight up into the air to avoid being hurt. It was
All right, so the car is moving at 30 miles per hour, and then the impact happens. Boom, and you're not going to see much of anything. All right, so what's happening here? Here's a real-life example. All right, so the amount of force acting on the person is going to be right at this is the point of impact. So the person is going to take the impact at 30 miles per hour. So what happens to the person upon getting hit? If the car is going at 30 miles per hour, what do you suppose is going to happen to the person? All right, so the person is getting hit right there. Person is getting hit right there. All right, the car is coming at you at 30 miles per hour. Upon getting hit, what do you suppose is going to happen to the impact point? How fast do you think it's going to be moving? Any ideas? Most of you guys are thinking, hey, the car hits you at 30, you're going to be moving at 30, right? I got news for you guys. Not really. That's your common sense talking. Your common sense is going to be like 99% of the time you're going to be wrong. So hopefully you guys are getting used to it. Notice that when I actually hit it, it gets out of the way. So look, when you hit it, I can move my hand in that direction right after the impact. I'm not going to be able to touch it again. You touch it once. As soon as you touch it, this thing is going to get out of the way at twice the speed of my hand. So if the car is moving at 30 miles per hour upon impact, the point of impact is going to move at double the speed of the car. If the car is moving at 30 miles per hour, point of impact is going to move at 60 miles per hour. If the car is moving at 60, the point of impact is going to move at 120 miles per hour. So whatever's getting hit is always going to move double the speed of the vehicle. This is known as the conservation of energy and momentum principle, something we're going to touch upon later on. Guys, here's the point of impact. At the point of impact, there's probably going to be 40,000 pounds of force acting on it. So what's going to happen to the point of impact? So that this point of impact is going to end up moving at double the speed of the car. So the force is acting on the point of impact. Center of mass is located here somewhere. There's no direct force acting on the center of mass. Notice that there's absolutely no force acting on the center of mass. Center of mass is free from direct force acting on it. So what does the center of mass do? It says, hey, in the absence of external force, center of mass is not going to move. So what's going to happen, the point of impact is going to get pushed in this direction. It's going to start to move in this direction at double the speed of the car. There's no net force acting on the center of mass. So entire body is going to spin with respect to the center of mass. All right, so the amount of force acting on the body, let's assume it's about 40,000 pounds. So according to Newton's third law, he should apply the same force back on the car. What's happening is kind of weird. This person is going to hug the car. That's a good thing. So, which means that the impact force is going to get dispersed onto a larger surface area. He's going to get projected in the upward direction, and that's going to make it survival. Notice that there's a huge dispersion of the force onto a larger surface area. And then he gets projected in the upward
up in the air, even higher than probably what he was even anticipating.
And so he's able to survive the impact as a result. All right, so the point of impact is going to take 40,000 pounds of force, guys. That means that his legs got shattered.
Police say the teenagers had
but he was able to survive.
been planning the stunt for 2 weeks.
Now, if a car is applying or exerting a 40,000 pounds of force on him, according to Newton's third law, he should be able to apply the same force back on the car. So what happens to the car if that's the case? Well, the action force is acting on him, which means that the reaction force is going to act on the car. Remember, guys, action and reaction forces are the same. They're in opposite directions. His mass is relatively small. The car's mass is relatively big. Same force acting on the bigger mass is going to cause a smaller acceleration. So the car initially is moving at 30 miles per hour, experiencing the same force. The car is going to slow down just a little bit. It's going to accelerate during impact. During impact, the car is going to go from 30 miles per hour to maybe about 29 to 28 miles per hour. That's what you would expect to see. The same amount of force acting back on the car implies that there's going to be a dent on the car. That's what you would expect.
The 16-year-old boy stood in front of his friend's car. He would have to jump several feet straight up into the air to avoid being hurt. It was impossible.
There was a car hitting here.
All right, so you got the action force acting on him. The reaction force is acting back on
Going
the
up
car.
in the air, even higher than probably what he was even anticipating on going.
And if you're
It
inside
was
the car,
impossible to
what do you
avoid
expect?
he would have to jump several feet. Stood in front of his friend's car. He would have to jump several feet straight up into the air. The 16-year-old boy stood in front of his friend's car.
And then threw him up in the air, even anticipating on going.
Well, there is more
It's not the first time Jackass fans have been hurt.
You can see the damage on the car, right? There's a tremendous amount of damage on the car.
When school let out, they
So the reaction force is going to act on the
brought
car.
the car to this side street across from the high school and got their cameras ready. One boy shot the accident from inside the
car is going to jerk.
Another taped it.
It's going to slow down a little bit.
In a nearby lawn. It's not the first time Jackass fans
and there's tremendous amount of damage on the
have been hurt trying to mimic
So you cannot mistake the reaction force in real
the
life.
types of stunts they see on the show.
All right, so taking to an extreme, the person in front of the train. So train is going to hit a person at 60 miles per hour. The amount of force acting on the person is going to be about 1 million pounds. So what do you think is going to happen to the person? Will the person splat, or the person is going to fly like a constipated bird? What do you think? Have you ever seen anyone get hit by a train in real life? All right, guys, we live in the Chicago area. It happens once or twice a year. It's a common thing, evidently. And sometimes people report seeing people getting hit by a train. All right, and when you do get hit by a train, I got news for you. You're not going to splat. It's just a myth. 1 million pounds of force acting on you, which means that you will splatter all over the place, especially if the train is going at 60 miles per hour. So torso goes one way, the legs, the arms, it just splatters all over the place. Now, no one denies that something bad happens to the person. All right, if 1 million pounds of force acting on the person, that implies that according to Newton's third law, person should also get to apply the same force back on the train. So the question is, does he really? Where's the evidence? I mean, you saw the person getting hit by a car. You saw the evidence on the car, guys. You saw the evidence on the car. The car got dented. If you're inside the car, you actually felt the jerk of the impact. But if you're on the train, it's not the same. You're reading a book, newspaper, texting someone. I don't know what you guys do usually on the train. If a train hits a person, if you're on the train, unless you see it happen, you will not even notice it. All right. If you see anything, you're probably going to end up seeing a head flying by. When was the last time you saw a head flying by? Hopefully never. You're not going to think to yourself, gee, I think we just hit someone because I saw a head flying by. You're going to think to yourself, look at that ball, which has a face on it. Now that the Halloween is coming up, I wonder where I can get one of those. That's your thinking pattern. So how is it that the person applies the same force back in the train, yet you don't feel it? It's 1 million pounds of force, guys. How does that even work? How does that even work out?
So the force is equal to mass times acceleration, right? So then, since the train is so massive, the acceleration will be minuscule in comparison.
Okay, yeah, give yourself 10 points for that one. That's not a bad way of looking at it. So let me make it a little bit more dramatic because that's what I like to do. So that when you're having a nightmare, there's a reason for it. All right, the train, the mass of the train, I tried to make it as big as possible. It's growing, cool. All right, train is really, 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 really massive. All right, so here's the mass of the train. I'm gonna put a big M in the middle. So the train is really, really, really massive. And in front of the train, I'm gonna put your mass. Okay, so I'll just put you right here somewhere. And this is you. Oh my God, this is so cute. All right, is it even gonna let me make this? Okay, so let me check to see if this works. This is you. That's awesome. All right, so here's the action force acting on you. This is gonna be 1 million pounds of action force. All right, so this is action force acting on you. And the same force is gonna be acting on the train. It becomes a reaction force in the opposite direction. All right, so reaction force is acting on the train. All right, so here's your mass. Okay, let me just put your mass. I cannot put the mass inside. We gotta make it very tiny. All right, so here's your mass. Do you see your mass? Oh, beautiful. This is your mass, and this is the mass of the train. All right, so what's happening is action force is acting on you. All right, so this is your mass. Okay, so we gotta just make this as big as possible. All right, so this is your mass. It's very small. And so the action force is gonna be acting on. Let me just get out of here. Action and reaction forces are the same. And let's get out. That's your mass. And here's the mass of the train. This is humongous. So as it so happens, because your mass is so little, your acceleration is going to be huge. This is your acceleration. All right, so this is the A. Small mass is going to accelerate. And the acceleration of the train is going to be extremely small as it so happens. All right, so the acceleration of the train is going to be very small. It's right here. Guys, forces are the same. Notice that the smaller mass is going to undergo the biggest acceleration. Literally, your body is going to go from 0 to 120 miles per hour within a fraction of a second. Train is probably about 50 million pounds, guys. A million pounds of force acting on it for a fraction of a second is going to cause a very small acceleration. Acceleration is going to be so small that the train is going to go, literally, it's going to go from 60 miles per hour to 59.9999 miles per hour for a fraction of a second. What does that feel like? It feels like a vibration. It feels like a vibration. Does the train ever vibrate? Of course it does, all the time. All right, so your life would be one of those vibrations. All right, that's the contribution of your life to the motion of the train. It's nothing. Acceleration is going to be so small, it's unnoticeably small. So Newton's third law still holds. For every single action force, there's going to be an opposite, equal and opposite reaction force, except the force acting on something which is so massive and the duration of the force is so short, it just caused an unnoticeably small acceleration. All right, so those people who made that comment, remark, give yourself 20 points. Okay, so that's the reason why. So that's what you would expect to see. Mathematically, it's going to work out the same way. All right, so in terms of math, here's what I want to do. That problem has that implication. All right, so what do we know? So we got a person jumping in front of a train. The train is moving at 60 miles per hour, right? All right, so the train is moving at 60 miles per hour. The amount of force acting on the person is going to be 375,000 newtons in the direction of motion. All right, so a couple of things, figure out the acceleration of the person, so we're interested in, and then the train, and then figure out the speed of the person as well as the train after impact. Okay, so what do we know? A couple of things we know. If the train is moving at 60 miles per hour, upon impact, we expect the person to move at double the speed of the train. So if the mathematics, if Newton's laws are correct, they should agree with what we expect, and what we expect is what we're able to measure. All right, so if the train is going at 60, person should be moving about 120. It's going to be slightly less, but more or less. Nevertheless, it's going to be about 120. Train speed is not going to change that much. It's still going to be about 60 miles per hour. It's probably going to be about 59.999. So that's what I expect to see. So that's what we got. I'm going to just cheat. Just grab this. Okay, so these are the formulas that, all right, so I'll just to the side, just want to make room. All right, so those are the formulas. That'll be useful. All right, so the force is going to be responsible for, the force is going to be generated in impact, so it's going to be responsible for the acceleration. During impact, the acceleration is going to change because you're going to be looking at broken bones, this and that, so it's going to be a chaotic motion, so average acceleration formula is going to be available for use in this problem. All right, so the first thing I'm going to do is I'm just going to list everything. All right, so I'm going to have the person here. Okay, so let's just go here. And I'm going to have the train here. All right, so what do we know? I know that the mass of the person is going to be 70. It says 70 kilograms, so that's the person's mass, and the train's mass is going to be 3 million. All right, so I got 70 kilograms here. And the train is going to be 3 million. All right, what else do I know? I know that the train is moving initially at 60 miles per hour. All right, so we got 60 here. So that's the speed of the train. So the train has an initial speed. And I also know that the person is not moving, so this is going to be 0. Person is not moving in the direction of motion. All right, so the train is moving, not the person. Okay, what else do we know? They will share an impact time. And this is 100th of a second impact time. All right, so what do we do? A and B, figure out the accelerations for the person and the train. So I want to know what these accelerations are. And for safety reasons, I'm going to express the acceleration in terms of g. And then let's figure out the speed of the person and the train right after impact. So what is the final speed? And obviously, it makes sense to express them in terms of miles per hour, because that's what we can relate to. All right, so we have only one single conversion, 60 miles per hour to meters per second. All right, so 26.78 or 79 meters per second is 60 miles per hour. That's it. All right, so find the person's acceleration as well as find the train's acceleration. Okay, so what do we have? Guys, this case is simple. Train hitting a person. You got the train, you got the person getting hit. So action force is going to be acting on the person. Reaction force is going to be acting on the train. It's going to be in the opposite direction. Acceleration is going to be caused by the action force acting on the person and the reaction force acting on the train. All right. Either way, acceleration is going to be caused by a force. Action and reaction forces. So force is going to be responsible for the acceleration. So acceleration is the same as force divided by mass. That's it. That's as far as this is going to go. All right, so what do we have for the person? A. All right, so the acceleration of the person is going to experience the impact force. All right, we don't have the impact force, so just copy down the impact force. Action and reaction forces is going to be the same. It's going to be 375,000 newtons. All right, so we got it. So the action force is acting on the person. It's going to be positive, divided by the mass of the person. All right, so what do you get for this one? Give me the number.
$5,357.14.
5,357.14 meters per second squared. Give yourself 5 points. Okay, I'm going to just move the decimal to the left. All right, so this is about 500 Gs. All right, guys, this is dead upon impact. In reality, the impact time is going to be shorter than this, but this is dead upon impact. Okay, so that's the acceleration of the person. What do we expect to see? We're getting the train. All right, so the reaction force is going to act on the train. All right, so it's exactly the same force, except it's going to be in the opposite direction. And it's going to be acting on a mass which is 300 million. All right, so what do we get here?
$0.12.
Negative.
All right, so it's going to be 0.12 in the negative. This is very small. I don't need to convert this to a G. It's meaningless. This is way too small. Okay, so I'm not going to even bother with that. All right, give yourself 5 points for that one. Okay, good. For those of you guys who came up with that number, give yourself 5 points. All right, so C and D. So what is the speed for C and D? Okay, so what do we know? We know that this is impact. What do we expect in impact normally? In impact, we expect the acceleration to change. So which means that we will get to use the average acceleration formula. All right, this, because we're estimating, we're trying to come up with an estimate for the acceleration. All right, so figure out the final speed based upon that. So I'm going to move my unknown to the left-hand side. And then just get rid of t. And then I'm going to add VO to both sides, so which means that I'm going to end up moving it to the right. So the final speed is going to be the same as the initial speed plus acceleration times time. Okay, so that's as far as we will go with this. All right. Part C, let's figure out the speed of the person. Okay, so what do we know? The initial speed of the person was 0. All right, so this is going to be 0. What that means is this person has an acceleration. What's the acceleration? The acceleration of this person is going to be 5,357.14. And the impact time, the duration of the impact is going to be 100th of a second. So the duration of the impact is here. Acceleration of this person is here. So you got to multiply those two. Is it 2/10? This is 100th of a second. Okay. So what do we get? This is going to be 1, 2. All right, so we end up getting 53.57 meters per second, right? Okay, convert this to miles per hour. And when you convert it to miles per hour, what do you get? All right, Lucy, give yourself 5 points for that one. Jack's same. All right, so multiply by, okay, very good. This is 119.99 miles per hour. All right, so Jack, give yourself 5 points for that one. So roughly 120. It's slightly under it. In real life, it's going to be almost 118 is probably where it's going to be. There's a reason for it, as you will find out. So what do we expect to see when it comes to the train? All right, so here's what we will see when it comes to the train. We expect about 60 miles per hour. Let's check to see if that's the case. expect about 60 miles per hour. So D is going to be the train. So let's do the train. So what do we know? Train is going to have an initial speed. Remember the initial speed of the train. That was 60 miles per hour. So this is 26.78 meters per second. Just a reminder. Okay, so I want to make sure when we are looking at these formulas, in essence, we're using the same formula for both of them. But remember, guys, the train is going to have a negative acceleration. All right, so the train's acceleration is negative. All right, so that's going to subtract from the speed. All right, so our initial speed is going to be 26.78 plus we have a negative acceleration, which is 0.12 times a very small impact time. Okay, so this term is going to get subtracted from that term. Okay, so I'm just guessing right now. Okay, but there's going to be a very small subtraction. So this is going to be 26.79. Okay, just give me the number. What do you have?
5.
Okay, it's going to be
26.75.
Say it again?
26.75.
75? Okay, not bad. All right, give yourself 5 points for that one. Okay, so just convert it to miles per hour. And then when you convert it to miles per hour, what do you get? Okay, so you end up getting, yeah, that's good. Lucy says 59.98. 59.98, roughly about 60 miles per hour, right? Okay, notice that it works out. Okay, so Newton's laws work in terms of explaining it. Okay, so it actually agrees with what we expect. In a sense, you expect the train speed is not going to change, and it doesn't. And you expect the people to move almost double the speed of the train. All right, so which means that the person do apply the same force back on the train. Except the train is just so much more massive, incredibly massive, that the acceleration of the train is unnoticeably small. So that's what happens. So what do we expect? The person getting hit by a train, you're gonna apply the same force back on the train. But because the train is so much more massive than the person who's getting hit, despite the fact that the forces are the same, because of the mass is so large that the acceleration of the train is going to be unnoticeably small. So head-on collision between a car and SUV, which one is going to experience a large impact force? It's going to be the same, right, for both of them. Except because the mass of the car is so much smaller than the mass of the SUV, the acceleration of the car is going to be much bigger. So which means that the car is going to suffer a lot more damage than the SUV.